Endeavor.
This is mission for its flight to the International Space Station. For its flight to the International Space Station. For its flight to the International Space Station.
Houston, Endeavor, roll program.
Roger, roll, Endeavor.
This is mission.
Houston, Endeavor, roll program.
Roger, roll, Endeavor.
This is mission for its flight to the International Space Station. For its flight to the International Space Station.
Seconds into the flight. The 3 liquid fuel main engines soon will throttle back to 72% of rated performance down in the bucket, reducing the stress on the shuttle as it goes transonic.
Go for main engine start. We have main engine start. 2, 1.
We're now making one last reach for the stars. We're now making one last reach for the stars. We're now making one last reach for the stars.
T-minus 10, 9, 8, 7, 6, 5, 3, 2.
Atlantis now on the proper alignment for its 8.5-minute ride to orbit, 4.5 million pounds of hardware and humans taking aim on the international outpost.
Is the process of manipulating a carrier wave to carry useful information, and amplitude modulation is when you change the amplitude of a waveform in order to transmit analog or digital information. I have an example here with my waveform generator that's putting out a 1 MHz sine wave that's being amplitude modulated at 1 Hz. Now this is what a frequency modulated waveform looks like. The amplitude stays the same, but we're changing the frequency. In this example, the carrier wave is 1 MHz, but we're slowly changing the frequency, so it's transitioning between 0.9 MHz and 1.1 MHz. We're doing the modulation here at 1 Hz, so it's nice and easy to see. And this is what it looks like at a more realistic frequency of 1 kHz. Be able to control the oscillation frequency so we can do frequency modulation. The type of circuit that we want here is called a voltage-controlled oscillator, or VCO. There are many different types of voltage-controlled oscillator circuits out there, but not all of them are suitable for FM radio. And there are many FM transmitter circuits out there, but in my experience most of them are very unstable, so I made my own. LEDs basically contain 2 specialized semiconductors that are stuck together, and when you apply a large enough voltage across them, they emit light from a process called electroluminescence. There is some heat produced, but overall the process is a lot more efficient, and you can get a lot of light from a very small device. On
Different types of electronic amplifiers. Can you recognize all of them? For instance, For instance, frequencies in the circuit's input are amplified more than others.
understanding the properties of a metallic glass made of 4 elements. The high-tech material made of zirconium, aluminum, copper, and nickel could have a wide array of practical future applications. This groundbreaking research could
How long have you had this problem? Is there any reason that you suppose that this started?
androgynous scene. It happened when it happened. Flying through the
This is an abstract shape. Shape belongs to all of these objects, but the shape itself.
From the sun's awesome furnace, from the deep bowels of the earth, nature's elemental forces have raged long before man's coming. Over the eons, man has feared their erratic, destructive power. He has offered up prayer.
Donut-shaped structure called the Io torus, a region of space filled with sulfur and oxygen atoms stripped of their electrons, formed of matter spewed forth by Jupiter's volcanic moon Io. Electromagnetic forces tie the torus to Jupiter's tilted magnetic field. Extending 5 million kilometers from Jupiter is a giant swirling disk of ionized gas called the plasma sheet. More than 100,000 kilometers thick, the plasma sheet is continually fed by matter from the Io torus and the icy Galilean satellites. Confining the torus and the plasma sheet is Jupiter's huge magnetic field, controlling a volume thousands of times larger than the Sun. Rotating with Jupiter, this giant structure is itself shaped by outside forces. If left undisturbed, Jupiter's magnetic field, like the Earth's, would resemble that of a giant bar magnet. But a supersonic ionized gas from the Sun, the solar wind, catches Jupiter's magnetic field lines and drives them back, away from the Sun. A shock wave is formed upstream from the magnetic field. The region inside the shock is known as Jupiter's magnetosphere. In 1988, after dropping a probe into Jupiter's atmosphere, NASA's Galileo spacecraft will begin orbiting the giant planet. One of its major tasks will be mapping the magnetosphere. Instruments on board will study Jupiter's magnetic field, its plasma sheet, and the Io torus. The first leg of the 22-month exploration takes Galileo deep into the magnetosphere. Here, a close-up view in the vicinity of the torus shows a high-energy proton spiraling around Jupiter's magnetic field, bouncing back and forth between Jupiter's north and south magnetic poles. During its mission, the orbiter will study the global structure of Jupiter's magnetosphere, mapping regions unexplored by any previous spacecraft.
The ultimate source of all energetic phenomena in the sun is the nuclear fusion of hydrogen understood. However, all indication of convection and rotation accelerates the convection zone near the equator and decelerates it near the poles. The magnetic fields that emanate from the lower boundary layer of the convection zone experience these shearing motions and become wound up and twisted. This amplifies the magnetic field and increases the magnetic pressure in the shear layer, which causes the gas pressure and density to drop and rise to the solar surface. The rope-like magnetic field then rises through the visible surface of the sun. When this occurs, the intense magnetic fields suppress the normal convection process, so that the surface areas in the magnetic region are cooler black and white, corresponding to the opposing polarities of the field. Turbulent convection continually stirs smaller magnetic concentrations over the entire solar surface. Here, we can see on a wide variety of scales that the magnetic fields are emerging and canceling. These more detailed images show the field canceling, or perhaps submerging back into the sun, are barely resolved with the best existing Earth-based solar observatories, having scales near 70 kilometers. Detailed simulations of such small magnetic flux tubes suggest that these bright points are formed by the magnetic field distorting flow of thermal radiation, and perhaps by directly heating the regions above them. The interaction of the convection and magnetic fields sends shock waves and photospheric plasma into the upper solar atmosphere. The emergence of magnetic field through the photosphere also heats the outer atmosphere. Response to the photospheric motions, explosive reconnection occurs, flinging material in our direction. Thus, the motion, emergence, and disappearance of magnetic fields in the photosphere control the heating and structure of the outer atmosphere of the sun. This theoretical recreation of one recent mass ejection shows its impact on the Earth's magnetosphere as it passes by. The changes in the Earth's magnetic shield disrupt our electrical and telecommunication systems. The recent demise of the Telstar 401 communications satellite is associated with this very mass ejection. During such events, charged particles that are normally deflected by our magnetosphere instead follow the magnetic field lines downward into the Earth's polar regions. These particles strike our atmosphere. High-resolution images reveal that bright points with will also increase. The dynamics of these solar storms, 150 million kilometers from the sun, are ultimately controlled by processes 200,000 kilometers below its surface. If we are to learn to live with the sun in our increasingly space-dependent worlds, we must understand the dynamics of the magnetic sun.
the sun. The gaseous ball is erupting, spewing particles of energy out into space at enormous velocities. In less than 10 minutes, X-rays from the flare will enter the Earth's environment. Soon will follow high and low energy protons, and then 2 to 4 days later, additional protons and a magnetic field are carried across space by the ever-blowing solar wind. The most visible evidence of solar flaring is the aurora borealis, the northern lights. Streamers of white, green, or red paint the sky to the north as electrons accelerated in Earth's disturbed magnetosphere plow into the upper atmosphere, colliding with nitrogen and oxygen molecules and atoms there. Most prominent in the Arctic, northern lights have been viewed from as far south as Mexico.
Thus the chiefs smoked the pipe in communion at the same time, uniting in fellowship.
neighboring particles are connected by line elements. In the course of time, neighboring particles move apart. We show this process by removing the connecting lines. Let's repeat the experiment using a different spatial perspective. Although the particles have broken away from one another, the volume is contracted onto the attractor. The particles get whirled around and completely jumbled through the movement on the attractor. In order to examine the breaking of their relative proximity on the attractor, we now expose 170 particles to the Lorentz system. Their relative proximity is shown by a line. Once more, we remove the connecting lines when neighboring particles have moved more than a certain distance away from one another. In a short time, all proximity has vanished. The system is said to have sensitive dependence with respect to small changes of initial conditions. In other words, minor fluctuations have major consequences. However, the system doesn't drive all the particles apart. It just jumbles them up completely. In this respect, it is similar to a kitchen blender mixing spices into dough. The sensitivity with respect to fluctuations of initial conditions and the mixing property has the effect that, in spite of strict determinism, their movements are practically unpredictable. The movement here is reminiscent of the eruption of lava masses. In the next two experiments, we look at how the Lorentz attractor is established by the Lorentz equations. The Lorentz equations are indeed based on parameters. We now vary one of the parameters, r, between the values of 1 and 28. We first examine the stability of the stationary points. By means of a small surrounding cube, we examine the stability of the spiral points. The parabola describes the path of the spiral points when r is altered. In the repeat, we see that the cube first contracts. In other words, the spiral point is stable until it reaches r equals 24, when it becomes unstable. This can be seen from the expansion of the cube, which at r equals 28 is finally whirled once more on the Lorentz attractor. Incidentally, the behavior of the second spiral point on the other branch of the parabola is exactly the same. The third stationary state of the Lorentz system is a saddle point for all parameters in question. Let's now look at the development of one branch of the unstable manifold of this saddle point. If we alter r, it first spirals into the spiral point and then develops into a homoclinic orbit at about r equals 13.9. At higher r values, the manifold turns towards the second spiral point. It finally forms a heteroclinic connection with an unstable limit cycle. R is about 24 here. If the parameter is further enlarged, the Lorentz attractor is finally stabilized at R equals 28. In our final experiment, we showed the Lorentz experiment, which made scientific history. This experiment shows how the chaotic properties of the attractor are tied up with the dynamics of one-dimensional mappings. On the left, we see a typical trajectory on the attractor. The attractor is put into space in such a way that the z-axis points upwards. The experiment consists of a simple measurement. Measurements are made of maxima in the direction of the z-axis, for example, now, and now, and now. We document our measurements on the right. We present each pair of successive maxima side by side as a point in the coordinate system, just as in the iteration of a mapping. In other words, we mark the value of the last maximum with an arrow on the abscissa. The greater the value, the further right is the arrow. We then register the value of the following maximum over the arrow. First, we see what appears to be the simple development of a curve based on the maxima. But a second branch also establishes itself, which, for example, measures the change from a very large to a very much smaller maximum. To summarize, we can see that the measurements in our diagram seem to constitute a simple graph of a one-dimensional mapping, whose iteration, then, would describe the distribution of the maxima along a trajectory on the Lorentz attractor. In fact, it is known that our measurement does not lead exactly to a graph of a mapping. Nevertheless, this experiment by Lorentz represents a decisive step forward in research into the chaotic